Hey everyone, Miss Anselmo here with a tutorial on bonding, reactions, and pH. Some background information you need in order to understand chemical bonding is the concept of valence electrons. For our last test, we learned that valence electrons are the electrons on the outermost energy level. One of the things that we learned related to bonding is that atoms would like to have a complete valence shell, meaning their outermost energy shell would like to be complete. For most atoms, this means 8 electrons. The only atoms that are full with 2 electrons would be hydrogen and helium, since they only have 1 electron shell. The rest of the atoms would like to have 8 electrons on their outermost shell. Most atoms don't have 8 electrons, so in order to accomplish this stable setting, they bond with other atoms. To help us better visualize what types of bonds atoms will make, we usually draw the atoms as Lewis dot structures. Now, if you look here, boron has an atomic number of 5, which means that it has 5 electrons. We learned for our last test that the electrons will organize 2 electrons on the first energy level, and then any remaining will go on to the next energy level. The energy levels above the first energy level will hold up to 8 electrons. Since boron only has 5 electrons, 2 will go on the first energy level and 3 will go on the next. Since the outer energy level or electron shell has 3 valence electrons, the Lewis dot structure will include the element symbol along with dots that represent the valence electrons. So the special thing about the Lewis dot structure is that it shows only the valence electrons. This helps scientists better visualize what types of chemical bonds will be formed. For example, if an atom has few electrons, it's likely to get rid of their electrons on the valence shell. If an atom has almost 8, the atom is more likely to just gain electrons in order to be complete. There are 2 types of chemical bonds. The 2 types of chemical bonds that we discussed in class include ionic bonds and covalent bonds. Ionic bonds are bonds that occur between a metal and a nonmetal atom. If you look at the periodic table here, sodium, or Na, is a metal, and chlorine, Cl, is a nonmetal. When these 2 atoms bond together, they form an ionic bond. Looking down underneath the periodic table, NaCl is the compound. 1 atom of sodium bonds with 1 atom of chlorine. One other characteristic of ionic bonds is that electrons are transferred from the metal to the nonmetal atom. Since the electron is transferred from one atom to the other, we end up with ions, hence the name ionic bonds. So in this example, sodium has 1 valence electron, so it's likely to lose that valence electron, and chlorine has 7 valence electrons, so it's likely to gain 1. The sodium atom gives its 1 valence electron to chlorine, so chlorine becomes a negative ion, sodium becomes a positive ion, and since opposites attract, the 2 ions come together to form an ionic bond. Covalent bonds are different than ionic bonds in that covalent bonds exist between 2 nonmetal atoms. One key idea to remember is that hydrogen, while it's on the left side of the periodic table, is actually a nonmetal. So here we're going to look at a bond between carbon and oxygen. Since both carbon and oxygen are nonmetals, a covalent bond will form between the 2 atoms. Now, with covalent bonds, electrons are not transferred. Electrons instead are shared between 2 atoms. This simply means that the 2 atoms will essentially overlap their outermost energy level and share electrons so that they each end up with complete outer shells. So if we look at carbon here, carbon has 4 valence electrons. I know this because I can see that carbon has 4 dots in the Lewis structure. So since carbon has 4 valence electrons, it would like to share 4 more to have that complete outer shell of 8 electrons. Each oxygen has 6 valence electrons, so each oxygen would like to share 2. So what happens is this oxygen will share 2 electrons with carbon, and this oxygen will share another 2 electrons with carbon. And what happens is the carbon and oxygen atoms will form covalent bonds by sharing 2 pairs of electrons each. To predict whether a bond is covalent or ionic, you simply have to look at the compound and look at which elements are present. Then you refer to the periodic table to determine whether the elements are 2 nonmetals or a metal and a nonmetal. So in the first example, I see CH4. Carbon is a nonmetal, and hydrogen, while it's on the left side of the periodic table, is also a nonmetal. So since carbon and hydrogen are both nonmetals, this would be a covalent bond. I'm going to show you that by just writing the letter C to save time. Lithium and fluorine, if we look at the periodic table, lithium is over here on the metal side and fluorine is over here on the nonmetal side. So since lithium is a metal and fluorine is a nonmetal, the bond will be an ionic bond. Sulfur and oxygen are both nonmetals. So since sulfur and oxygen are both nonmetals, the bond will be a covalent bond. And lastly, we have potassium and bromine. Potassium is a metal and bromine is a nonmetal. So since potassium and bromine are opposites, one is a metal and one is a nonmetal, the bond is an ionic bond. So again, to tell whether it's a bond that is covalent or ionic, just look at the periodic table and determine whether you're dealing with two nonmetals, which would be covalent, or a metal and a nonmetal, which would be ionic. Chemical reactions are written to show you which substances bond with which other substances to form something new. Chemical reactions have two sides. On the left side, you have the substances that we call reactants, and on the right side, you have substances that are called products. The reactants are the substances that will react, the atoms will rearrange, and the new substance is called the products. When looking at a chemical reaction, we often need to count the atoms to figure out what the chemical reaction is actually showing us. When we count atoms, we have more than just the element symbol showing. Sometimes there will be a number in the front, which we call a coefficient, and sometimes there are numbers down here written as a subscript. Anytime a subscript is written next to an element, that subscript belongs to only that element. However, a coefficient written in the front belongs to every atom that follows it. For example, on this side, we have a 2 in front of the H2O. That 2 means that there are two H2O molecules. So that 2 essentially distributes, almost like in math, to both the hydrogen and the oxygen. Counting atoms, if we look at the left, this 2H2 here, shows that there are 4 hydrogens. The reason there are 4 hydrogens is because a single H2 means that there are 2 hydrogens, but the coefficient in the front is telling me that I actually have 2 H2s. So essentially the coefficient multiplies the subscript and we end up with 4 hydrogens. Here I have O2 written with no coefficient in front of it. Anytime there's no coefficient, you just assume that there's a 1 there. So since we have 1 molecule of O2, there are 2 oxygens. Over here I have 2 H2Os. Again, the coefficient multiplies the subscript, so that means that I do 2 times 2, which gives me 4 oxygens. But remember, the coefficient also spills over to the next atom as well. So since there are 2 H2Os, there are 2 total oxygens. Let's take a look at another example that's a little more complicated. If I look at the reactant side of this equation first, I note that there are 3 total carbons, 8 total hydrogens, and 10 total oxygens. The 10 comes because there's a coefficient of 5 and a subscript of 2. So we multiply the 5 times the 2 to get 10 total oxygens. On the product side, we see that there are still 3 carbons because of the 3 coefficient in front of the C. I have 8 hydrogens because of the coefficient of 4 in front of the H2, so the 4 multiplies the 2. And I have a total of 10 oxygen. Now the oxygens are split up here. I have a coefficient of 3 with an O2 here. So the 3 multiplies the 2 to make 6 oxygens. But over here I have another 4 oxygens because of this coefficient here. So I take the 6 oxygens from here and add them to the 4 oxygens there to get a total of 10 oxygens. If we look at this chemical equation, we can see that the number of atoms on the left is equal to the number of atoms on the right. The number of atoms of each element is also equal. This represents a balanced chemical equation. The idea of a balanced chemical equation leads us to the law of conservation of mass. The law of conservation of mass states that matter can neither be created nor destroyed. Now that's a very fancy sentence, but essentially it means that the number of atoms of each element must be the same on each side of the chemical equation, which is exactly what we just saw on the previous slide. There are 4 different types of chemical reactions. We have synthesis, decomposition, single replacement, and double replacement. Synthesis involves the combining of 2 substances to form something new and big. Decomposition is when a substance breaks down into 2 simpler components. Single replacement is when one component of an atom is replaced by another. So in this example, you can see that the B is replaced by the C. And double replacement is when 2 elements are replaced. Essentially, the 2 atoms switch partners. So if we look at the A and the D, A switched partners with D, and A ends up being bonded with C, and D ends up being bonded with B. That's an example of a double replacement reaction. Here are some examples of what these reactions look like with actual chemicals. So synthesis over here, we see sodium and chlorine combine to form sodium chloride. For decomposition, that's when a substance breaks down. We have H2O, or water, breaks down into hydrogen and oxygen. Single replacement is when one atom is replaced. So if we look, we have HCl here. So essentially the Al and the H switch places, and that's a single replacement. And here we have a double replacement. We have HCl and NaOH, each switch partners. So the Na and the Cl will combine, and the H and the OH will combine to form water. Finally, we have acids and bases. With acids and bases, one of the most important things to understand is the pH scale. The pH scale is a scale of numbers that goes from 0 to 14, and it helps us identify substances as acid, base, or neutral. Looking at this pH scale, you can see that acids have pHs that are lower than 7. And bases, I'm going to write bases up here. Bases and alkaline are basically the same thing. Sometimes they call it alkaline, sometimes they call it bases. But bases are any substance with a pH greater than 7. So the magic number here to remember is 7. And the number 7 itself represents a neutral substance. So if a substance has a pH of 7, it's neutral. If the pH is below 7, it's acidic. And if the pH is above 7, it's basic or alkaline. Now, as you move away from the number 7, the substance gets stronger and stronger. So a pH of 6 means that you are dealing with an acid, but it's not a very strong acid because it's still close to neutral. However, if you have a substance with a pH of 1, that would be a very strong acid. Same thing with bases. A base that has a pH of 8 is not a very strong base because it's still close to neutral. However, a substance with a pH of 13 would be considered a very strong base. Here are some properties of acids and bases. On the left, you'll notice that there are some properties of acids that include conducting electricity and having a sour taste. Properties of bases. Bases also conduct electricity, but bases don't have a sour taste. They actually have a bitter taste, and they're slippery when you feel them. Examples of acids include things like lemon and vinegar, and bases are usually things that we use for cleaning, like soaps and detergents. When it comes to acids and bases, we use indicators to help us determine whether we're looking at an acid or a base when we're testing a solution. One of the easiest indicators to use is litmus paper. There are 2 types of litmus paper. We have red litmus paper and blue. When red litmus paper is put into a solution and it turns blue, that indicates that there is a base present. If a blue piece of litmus paper is put into a solution and it turns red, that means that you're dealing with an acid. If red litmus paper stays red and blue litmus paper stays blue in the same substance, you're dealing with something neutral like water. Litmus paper helps us determine whether an acid or a base is present, but pH paper is an even better indicator because it helps us determine the actual pH of a substance. pH paper works similar to litmus paper, except there's an entire range of color. You can see here that we refer to a color chart when we dunk our pH paper into a substance. The pH paper will change color, and then you compare the color to the chart to determine the pH of the substance. Similar to pH paper is cabbage juice, and this was actually a lab that we did in class. Cabbage juice is generally purple in color. You have to use the red or purple cabbage to create the juice. And cabbage juice has an interesting property in which it changes color in different acids. At the top is a color chart for cabbage juice in different pH substances. At the bottom is an example of what we saw in class. In fact, this is a student picture. So the pH of a substance will change the color of cabbage juice, and whatever color the cabbage juice changes will help you identify the pH of the substance. substance. So for example, this substance on the very right has a bluish color, and I would say that that substance is probably a pH of about 6, whereas this substance here has a pinkish purple color and probably has a pH closer to 4. That's all for bonding, reactions, and acids and bases. Thanks for watching.